There is a rocket engine that, on paper, beats almost every other one. NASA built it and successfully tested it. It was a candidate for powering the space shuttle. Over $1 billion went into its development. Still, in 70 years, this engine has never flown into space even once. It's called Aerospike, and to this day, it's considered the holy grail of rocket engineering, because every rocket you've ever seen launch flies with a built-in weakness: a compromise that wastes fuel. The Aerospike doesn't have this compromise, so why isn't it flying everywhere by now? This is a story about a curse that has swallowed up programs, companies, and billions of dollars. And about why this curse is being broken right now by a German startup over the Baltic Sea, from Spain with a 3D printer, and from a rocket that is supposed to launch this year from America's oldest launch site. My name is Sirwan, and this is Mars Chronicles. To understand the Aerospike, we first need to talk briefly about the good old bell nozzle that's attached to every rocket. Its task sounds simple. It is supposed to direct the hot exhaust from the combustion chamber in one direction and convert as much pressure as possible into thrust. The problem is the air pressure around it. A nozzle only works perfectly when the pressure of the exhaust gas at the end of the nozzle exactly matches the ambient pressure. And that changes dramatically during ascent, from full atmospheric pressure on the ground to a vacuum in space. However, a rigid bell can only be optimally shaped for a single altitude. That's why it's generally too large at ground level. The surrounding air compresses the exhaust jet. In a vacuum, it's then too small. The gas expands out to the sides and dissipates uselessly. So every bell nozzle is a compromise, and this compromise constantly costs performance on the way up. That's exactly why rockets like the Falcon 9 have short nozzles at the bottom and huge ones at the top in the vacuum stage. You simply build two different compromises. The Aerospike solves this problem with a brilliantly simple trick. It turns the nozzle inside out. Instead of channeling the exhaust through a bell on the inside, it flows along the outside of a central spike or ramp, the spike that gives it its name. On one side, the jet is pressed against the spike. On the other side, it's only limited by the surrounding air itself, and that's the trick. The atmosphere becomes the missing nozzle wall. Because the air pressure changes with altitude, it automatically shapes the exhaust jet exactly right every time. At ground level, the dense air presses the jet tightly against the spike. In a vacuum, it can spread out widely, so the engine automatically adapts to any altitude, all without moving parts. This is called altitude compensation. According to figures from the European Space Agency (ESA), it promises up to 15% more efficiency. That may not sound like much, but in space travel, it's huge, because 15% less fuel waste directly translates into more payload in orbit. By the way, that also explains the strange name. Because a fully formed spike would be very long and heavy, in practice, it's cut off. And instead, some gas is blown into the center of the truncated base. This cushion of gas aerodynamically replaces the missing tip. It's basically a spike made of air. Aerospike, the Airspike, and as a little bonus, the spike comes in two flavors. Ring-shaped, where the combustion chambers are arranged in a circle around a central cone, and linear, where they fire in two lines along a flat ramp, which looks like the back of a spaceship from a science fiction movie. No wonder fans said that the most famous Aerospike project looked like the Millennium Falcon. Which brings us to the story, and it's nothing but drama. The concept has been researched since the 1950s, among others, at Rocketdyne, the engine manufacturer behind the Apollo engines. In the 1960s and 70s, they built ring-shaped Aerospike versions of the J2 there, which is the upper stage engine of the Saturn V. And they successfully fired them on the ground. The Aerospike was even a serious candidate for the main engine of the space shuttle. It lost. Too new, too risky, not tested enough. The big moment came in the 1990s. NASA wanted a shuttle successor that could reach orbit in a single stage, the legendary VentureStar project from Lockheed Martin. And a spaceplane that has to go from a standstill to orbit on a single tank of fuel needs an engine that's efficient at every altitude. The perfect job for the Aerospike. The X-33 was built as a test vehicle, and for it, Rocketdyne developed their favorite project, the linear Aerospike engine XRS 2200. Its core, the turbopumps, came directly from the J2 of the Saturn V. And this engine worked. Around 93 tons of thrust at sea level, about 121 tons in vacuum. Over a dozen successful test runs at the Stennis Space Center. In August 2001, there was even a double test with two coupled engines for over 90 seconds. NASA even strapped a test model onto the back of an SR-71 Blackbird to measure the aerodynamics during supersonic flight. An Aerospike on the fastest plane in the world. However, it was never ignited, and then the program died anyway. Not because of the engine, which worked, but because of the composite hydrogen tank, which failed spectacularly during a pressure test in 1999, and it proved unmanageable. In 2001, NASA pulled the plug. Over $1.2 billion had been burned, and the finished Aerospike engines ended up in a museum. After that, no one seriously dared to try again for a long time. Firefly wanted to build its first rocket with an Aerospike and went bankrupt before it ever flew. The successor company immediately scrapped the Aerospike. Other announcements came to nothing. The curse of the Aerospike became a catchphrase, but there's no magic behind it, just a very concrete problem. The cooling. With a Bell nozzle, the wall is on the outside of the jet. With the Aerospike, the spike sits right in the middle of the fire, surrounded on all sides by exhaust gases hotter than 3,000 degrees, and the tip is the hottest point of all. Cooling that thing without it melting or becoming absurdly heavy has worn down generations of engineers. This is exactly where the turning point comes in, and more on that in a moment. In recent years, something has happened that changes the rules of the game. 3D printing, or more precisely, additive manufacturing. The cooling problem of the Aerospike is mainly a manufacturing problem. You need hundreds of fine cooling channels that wind their way through the spike into the chamber walls. And that was hardly affordable to build with traditional milling and welding. A modern metal printer simply prints these channels right into the part. From high-performance copper alloys in a single piece, and suddenly teams all over the world are trying it again. The Spaniards from Pangea Aerospace in Barcelona fired their demo P1 on the test stand of the German Aerospace Center in Lampertshausen in November 2021. The world's first Aerospike engine that runs on methane and oxygen, printed from a copper alloy developed by NASA. Around 2 tons of thrust. Ignition on the first try. A 2.5-minute run. In the meantime, they're developing the big successor, Arcos, a ring-shaped Aerospike engine for upper stages, which has grown from the originally planned 30 tons of thrust to now around 76 tons. And with millions in Spanish funding, it is set to become the world's first flight-ready Aerospike. Especially elegant, Arcos doesn't steer the thrust with heavy swivel mechanisms, but by throttling the individual combustion chambers in the ring to different degrees. No moving parts here either. A German startup has gone even further. Polaris Spaceplanes from Bremen. They are building small spaceplane demonstrators with a self-developed 3D printed linear Aerospike called AS1 on the 29th. On October 29, 2024, their 5-meter-long Jet Mirror 2 ignited this engine in flight over the Baltic Sea. According to the company, this was the world's first ever ignition of a linear Aerospike rocket engine in flight. And now, let me tell you where this happened, near Peenemünde. There, where the V2 was once developed, today, the engine that NASA failed at is flying. Polaris has now completed over 250 flights, completed with 7 demonstrators, and received a contract from the German Armed Forces in January 2026. To build a reusable supersonic test aircraft the size of a fighter jet, powered by 2 turbofans and the Aerospike, ready for flight by the end of 2027. What I especially like here are the ambitious timelines. Germany is currently leading the world in flying aerospikes. And then there's another connection that might sound familiar to you. Leap 71. The company founded by Josephine Lissner and Lynn Kaiser, whom you know from our video, has set their engineering AI neuron to work on exactly this problem. In December 2024, they fired a completely computer-designed, monolithically printed Aerospike with half a ton of thrust. It worked on the first try. A year later, in December 2025, they brought an orbital-capable 2-ton Aerospike using methane and oxygen from specification to first ignition in under 3 weeks. The decades-old cooling problem that has broken billion-dollar programs is now being iterated by algorithms and printers on a weekly basis. If you're as fascinated by this as I am, feel free to give the video a like. It's just one click for you, but it helps the channel a lot because YouTube will show the video to many more people. And in the channel memberships and in the shop, there are some nice extras waiting for experts. Let's get to the crucial question of this video. And maybe you've already asked yourself this: what about Stokes Space? We've dedicated 2 separate videos to the company, which I'll link below. Their rocket, Nova, is one of the most exciting projects in the industry. Fully reusable, both stages. And their upper stage looks suspiciously like an Aerospike, a ring of 24 small combustion chambers with hydrogen and oxygen, arranged around a central, actively cooled metallic shield, with gas flowing out from its center. So, is this an Aerospike? The honest answer is a definite yes and no. And the yes and no is the most interesting part about it. Stokes itself describes it as the central gas flow, creating an Aerospike-like effect. So the altitude compensation is a welcome bonus, but the actual purpose of this central shield is something completely different. It's the heat shield for re-entry. Instead of covering the upper stage with sensitive ceramic tiles like the Space Shuttle or Starship do, Nova returns with its tail first and simply holds its liquid-cooled engine base into the heat of re-entry. For this, they use liquid hydrogen. The same cooling channels that protect the metal from its own flame during launch also protect it during re-entry. That's the real genius. Stokes not only solved the cooling problem of the Aerospike, they made it their business model. And the timing could hardly be better. The first stage, with its 7 Zenith engines, by the way, full-flow staged combustion like the Raptor, completed its qualification tests at the beginning of June 2026. And the maiden flight is planned for the end of 2026 of all places, from Launch Complex 14 at the Cape. The pad from which John Glenn flew into orbit in 1962 as the first American. There's still one distinction that often gets mixed up. Let's clear that up quickly now. Aerospike and rotating detonation engines, or RDEs for short, are often lumped together because both are considered the miracle engines of the future and both often have a ring-shaped appearance. But they solve 2 completely different problems. The RDE changes how the fuel burns, namely in a rotating detonation wave instead of a steady flame, and it gains its efficiency from the thermodynamics of the combustion itself. The Aerospike changes how the exhaust expands. It gets its advantage from the aerodynamics of the nozzle. One happens before the nozzle, the other is the nozzle itself. And because they work on different aspects, they are not mutually exclusive. On the contrary, a ring-shaped detonation chamber and a central spike actually fit together suspiciously well, geometrically speaking. And exactly these kinds of combinations are already being explored in research. If you want to dive deeper into detonation engines, our videos on the topic are linked below. Finally, here's my honest assessment. The Aerospike is not a miracle solution, and it comes decades too late for its original dream. The main driving force back then, the single-stage spaceplane, is practically dead today. Because reusable 2-stage rockets like the Falcon 9 and Starship have solved the cost problem in a different way. That 15% efficiency gain is real. But a Bell nozzle is cheaper, lighter, and has been proven thousands of times, and every new technology has to fight against this argument. And yet, I believe that the Aerospike is finally becoming a reality. Just through the back door, not as the main engine of a glorious spaceplane, but in places where its unique features suddenly become worth their weight in gold. As an upper stage engine like on Pangaea, where altitude compensation directly increases payload. In supersonic flight, like on Polaris, where a flat integrated engine fits perfectly into an aircraft fuselage. And as a reusable heat shield like on Stokes, where the cooled spike does two jobs at once. After 70 years of being cursed, in the end, it's not the most beautiful theory that wins, but the most pragmatic use case. And when a Nova lifts off from the John Glenn launch pad at the end of this year, something will be flying for the first time that generations of engineers considered cursed. I will be watching, and hopefully you will be with me. My name is Serwin, and this was Mars Chronicles. Thank you for tuning in. Per asperar ad astra.